Okay, good morning. We're officially on the week of Thanksgiving on our Monday class, and I'm just going to start by bringing up the calendar again and reviewing the steps that we're into. We're here on the 22nd, and we have the 29th and the 6th as our remaining lecture times. And then we'll have the 13th as finals week. And my intent, again, I'm going to work this backwards. My intent, again, I'll come in on the 13th. You'll already be working on the final exam / project. And we'll have any discussion on that. And I'll set a due date, maybe Thursday or sometime during that week, depending upon where things are at. And that will... the old version of the exam is actually posted right now, but I'm reserved the right to make changes. I know I need to make some changes to it. Backing up from there, though, I promised one more homework assignment, and looking at my records, I actually had 2 assignments, but I can put everything on one sheet. We had the remaining problems from Chapter 9 that we're into right now, and then we jump over 10. And 11 is information theory and coding. So I've always had a few problems from that chapter. They're kind of like the take-home exam problems. They're not very hard. And I know, Joseph, you were surprised at how easy the problems are, but they were designed for this in-class exam. They were designed for an in-class exam where you had just a finite amount of time and had to work quickly. So I didn't change that. I kept it the same as I've had it. And so when you see that, or when you saw that last night, I guess, and you were messaging to me, it's like, yeah, I don't have to spend very much time on this because that was the intent. But I will be getting problem set number 6 out there, and I'm going to wait till later today after I've thought about what we've done today and where I think we're going to end up in this class. This class is not... It's going along just fine, except for me not grading papers. It's going along just fine. It's very predictable. You two are very predictable, and we're just kind of humming away. My other class, I kind of don't know where I'm going to end up because of the fact that things have been challenging to me. So it's a lot more delicate in how I deal with the end. And I feel like right now I could have the whole thing blow up in my face because of the fact that I have more stuff I want to do, and I'm having a very hard time dealing with the thought of not being able to do certain things just because I'm getting pushback. They're not pushing back at me literally, but they're kind of just being sluggish and so I don't know. If you were in my situation, you might do what I'm tempted to do, and that is just push forward, give everything out, and if nothing gets done or nothing gets done very well, so be it. I'll have the numbers, and then I get to decide how I do the grading. So I did repost the exam from last week because I got information about problem number 4 finalized, and that took me a lot of time to get that to work right. I had some coding error that I could not see. It confounded me endlessly. I mean, if I was holding up my fingers, I was that close to pulling the problem, saying, I just can't keep spending time like this, because we talk about it in class, I get excited about it, you're excited about it, and then I go out to try to make something happen, and I kind of burn myself out not getting it to work quickly, and I'm spending hours and hours doing that. So don't ever think that I don't spend hours and hours working on stuff, because I do. And if you're frustrated that you maybe don't get something right away, perseverance is kind of the order of the day. You understand that? I mean, that's just the way it can be, especially when you're coding a simulation. But eventually things happen, and the other really significant thing is that things have a way of happening not when you're expecting them to happen, because you beat on something, try to make it work, you eventually set it down saying, I'm going to have to come back to this, and that process of setting it aside and keeping to think about it, you eventually, when next time you look at it, something jumps off the page and you see exactly what you're doing wrong.
I did have a couple of questions on the DFE problem.
Yeah, we're gonna do that right now. So I don't know if that ever happens to any of you where you set something aside because you just can't get it. You'd like to get it before a meal, before bed, before walking outside for me because I take exercise breaks. But sometimes you just have to leave it and then come back. And that happens a lot for me. So on the exam, I'm just going to start at the top. Since you asked about this one, Joseph, I think I answered your question okay, or at least you sounded like you did. I just want, you can put the equations in here that you're using. You can reference where you're getting the stuff from the book and then just give me the answers. And if it's like not obvious which is the best, just clarify it and make sure I understand that you understand. You're not like elementary school where you just copy the answer and put it in there. You got to have a little bit of backup on there. And so words is fine. And also this sheet, you can use it and scan it and then have the computer problems done in a Jupyter Notebook and attach those, or you can do everything in the Jupyter Notebook however you want to do it. My other class, they've got a couple of computer-related problems, and I'm using my tablet to write the answers out in these spaces, and I'll probably do that for this one, but it's just depends upon what you would like to do. This one is the same. It requires at best root finding. When I did this as a take-home exam, or as an in-class exam, you can't do as much, but I expect because you are doing this as a take-home, you can do this precisely, right, using the root finding technique. This one, again, is pretty straightforward. So on the DFE, the code example that I'm showing here, well, the first thing in the DFE problem is, and this is something that could show up in the final, it may show up in set number 6, is using, let's see if I can get this, is using these two functions, which we haven't played with yet. These are in the Digital Comm module. They're some of my most recent additions, and I wanted you to use this as an opportunity to get familiar with them because it makes it really nice to do MRE stuff. There's the PSK gray encode. There's also the QAM gray encode and corresponding decode. So in this case, you're only going to use MPSK, but I might have you do something with the QAM encode and decode. And what's nice about these functions is if you go look at how they work, they don't work at the symbol level. The other functions that we've used in class work at the symbol level. So you put in an input and you get out symbols as indices that are numbers 0, 1, 2, whatever, 3, 4, 5, corresponding to the symbols in the MPSK or points in the QAM constellation. This one works with the actual encoding and decoding, so it's actually always going to return a reference bit stream that's the bits that were generated. So data over here is a serial bit stream. So if we're putting in a mod type of 4 and we're asking for 100, I guess I have to look at this to make sure I think it's right. That's bits, right? Or no, symbols. So if you put in 100 symbols, you're going to get 200 data bits coming out. If you were to put in 8, you'd get 300 and so on and so forth, which makes sense, right? Yeah. The way I set it up. And then when you go ahead and decode over here, you give it a complex baseband set of samples that would be the I and Q values from the optimum sampling instant. And what it will then return is a bit stream that will correspond to the detection level. And now, because of filtering that still is going on, processing the channel filter, match filter, and so on, the bits that come out of here, data hat, are not time aligned with the ones that went in. They're going to be shifted to the right slightly because of the propagation and going through the filters. But the bit errors function there takes data and data hat, and it's synchronized. Remember, we talked about that. It looks for the correlation, and it brings them into alignment and automatically removes the ends as needed, or trims things automatically. I originally wasn't going to use that, and then I said, oh, I guess I'll do that, because it's a pain. If you have to do that manually, it's a pain to have to get that alignment done. So that's kind of the reason why I wrote the function.
Making an eye diagram to figure out where my alignment should be.
Oh, the sampling instant?
Yeah.
Yeah, and that you still have to do manually, because I'm not having you do the synchronizer on it. But
Yeah.
so I just thought I'd give you a little overview of that. So what I did in this little sample code, which you can copy out of the PDF here, I just wanted to exercise what's going on with these functions and then take it through the process that you will need to put in the DFE, where you have to go for the error, and then you're taking the constellation values, which is an array, and subtracting that from a scalar, a complex scalar, and then you're going to get the DFE error, and then you're going to find the index and the minimum error. The index is used to then find the estimate of the symbol, which needs to be made an integer so that you can use it. Well, I made it an integer so that I can, well, it needs to be an integer because it's an index. So this function min and argmin does not return an integer. So this was a necessity, actually. You understand that? Because an index into an array can't be a float. And you can just wrap int around that, and that will convert it to an integer. At any rate, then d hat are those symbol values that you're going to use in the decoder, and then the error detection and so on. This has to be wrapped up inside of the function. So I wrapped it up, and this is the function call that I created. So there's things that I want you to, I want you to use the same kind of interface, because that way I can look at it and see what you've done more readily rather than you just inventing your own interface. So I started with let's see. I started with this shape PSK DFE equalizer, and then I added some more inputs into it. I chose to just add them on the command line to the function rather than put them in the data structure, because I decided that way it's kind of hackish, but it's easier for you to just do that. You can just push new variables into the command line of the function, and that's what I did here. So I added this argument to control the mod level, whether it's 2 or 4. This next one is just, I decided I wanted to have you experiment with the phase rotation, because I think we talked about that. Does the equalizer, can it take a constellation that has a static phase error, and can it fix it? And it can. And then I also added another attribute down at the end called DFE, and it's just a Boolean, so it's set by default equal to true, but that's because I put in my code switches so that if that's true, it's going to run the DFE, and if it's false, it's going to run the decision directed. And I kind of explained by inference again how I'm doing that. And that was, let's see, I added this hint later, and that's what that switch is actually doing. It's saying if I'm running decision directed, I'm going to initialize the A optimum array inside to have n zeros and a 1 in the middle, I'm going to keep this at the end, but I'm never going to use those coefficients. They're just going to be along for the ride, and I will never use them. It was just part of the topology I wanted to go with. And then if I'm in DFE, then I'm back to what the existing code was. I have n zeros, the current value initialized to 1, and then I have m zeros for the DFE. And there's a number of things you have to do in the code to switch things on and off. In the case of the gradient descent algorithm, these coefficients may take on values after you do the gradient descent with this long vector, but all you have to do right after it computes the updated coefficients, you just have to reset those end coefficients back to 0 again, and it will ignore them. Does that make sense?
Yeah, that's what I was doing.
Okay, good.
Yeah, I
I'd
did
say
the
thumbs
gradient
up.
descent, and then I did like if not DFE, reset all of them back to 0.
Yeah, exactly. Otherwise, it will try to do something, but it's like no, we don't want to do all this. We want to do this or that. We don't want to try to clobber it all up. But it's just kind of a way of prototyping where you just keep massaging it quickly. And that's my strategy when I'm writing code. I would clean things up later, but I decided I would just do it quickly because, like I said, I was really close to bailing out on this because it was taking me forever to get it working. And I didn't really want to give it to you until I had it working because I'm like, I've created a monster and now I absolutely have to get this thing to work, whereas I could bail out before I threw it at you and made you suffer through it. So
I did have a question.
yeah, I wanted to go through all that preamble. So here's where we're at.
So I have a problem with my code, and I was wondering if you had a guess as to why it might be.
Okay.
But maybe not. So right now my filters fix the rotation.
Right.
But I still have pretty big clouds around each of the 4 decision points.
Okay.
So I wonder, do you think that's the case of I'm missampling, or these cloud sizes don't change much with different SNRs? So I assume that it's an issue of I'm
Timing.
sampling at the wrong. I assume it's
Yeah.
a timing issue.
Yeah.
Is there a good way to investigate that?
Well, yeah. I mean, there's good ways to do everything. I did a lot of troubleshooting though, and I did things like that myself. So, if you say it's able to derotate properly, this right here was no equalization, and this was an SNR of 20. So, what we're seeing here is a combination of ISI, but we're also seeing some due to the 20 dB on the channel. So you can selectively do things. So first off, what I would do is I would make the SNR be about 50 dB
Yeah,
or higher.
I bumped that up. I did like 1,000 SNR.
Okay, so it's out of the
So
picture.
it derotated, and I still have pretty big clouds.
Yeah.
So I
Okay.
assume I'm getting some ISI.
And
What?
Do you plot the exactly Z parameters? You should plot the Z parameters, because these figures, this last figure is for output of equalizer.
Wait, so you mean at the sampled instances, like
Yeah,
every
maybe
NS?
Maybe you plot the input of equalizer, because I have this problem.
and you resolved it, so it's working for you.
Yeah, and I found out my mistake was in plotting my mistake was plotting different parameters.
Okay.
I should plot because these figures are for output of.
Yeah, I want to show you something else that I kind of did all along too. That I'm back in the code. That's kind of a cheesy thing that I did.
So
Pardon
are
me?
Are you using the match filter?
Yes.
And you do that. It looks like you do the match filter before your DFE.
That's right.
And
So
that's-
I want to explain something though that I probably never really explained. The first thing, here's the match filter, the distortion filter. You can turn it off. That's another thing you can do. If you just simply comment that line out, X will just run down, get noise added to it, and we'll go into the match filter. and then get sent off to the LMS algorithm. So that's another thing that you can do. You can just turn off the distortion filter temporarily. But one of the things I did here, which I think is a little bit hokey, but it was something that I wanted to do when I created this, and that is when I go into the LMS algorithm, I'm sending in, this is a symbol-spaced equalizer. It's not fractionally spaced. That's another option I have on the table for the final two, is do something with fractionally spaced, because I found some of that in one of my old papers. But I send it only the symbol samples, and those have to be right. So you're right in looking at your timing, because that is the starting point. And if you're not sampling at what you think is the best point, it'll still try to work with it, but it's better to make sure it's as good as possible. If it was a fractionally spaced equalizer where you'd be taking, say 2 samples per symbol or 3 or 4, then the equalizer has a lot more information. Because one of the things they didn't talk about, which is in the books, it's probably in that chapter actually, because there's a section in there, the chapter that I put from that book on Slack, the fractionally spaced. It's like aliasing. And what happens when you only sample once per symbol, there's information that gets folded because you're downsampling and you're going to create aliasing for sure. But that's the nature of the symbol-spaced equalizer. You get the best samples you can, and then you have some aliasing that takes place. But one of the things I did in order to make it look like you could still see it at the oversampled rate is I have this just find the optimum filter coefficients, and they're contained inside of the structure, right? So if you go down to the bottom, we know A output, or whatever I call it, DFE outputs contains A opt inside of there. It also contains the error. It also contains the simple sampled equalizer values and hard decision data that comes out of the decision-making device, not all of which I use, but because I wanted to have a waveform so that you can do an I-pattern plot from it, what I did up here is after we return from that, then I pretend that I have the equalizer filter, but I'm going to upsample it by a factor of whatever, 10. So I'm upsampling it, which means that upsample operation in here is 0 padding into the array. And so now I can use that filter as a smoothing filter or equalizer filter on the original signal Z that came out of the matched filter. And that was just so that we could have a waveform to look at. Otherwise, you wouldn't be able to do the I-pattern plot. The scatter plot, yes, because you can always do that at the symbol spacings. But if you wanted to actually see a waveform, then I'm upsampling. I'm not using an interpolator. I'm just letting that filter be, it'll interpolate without, won't have non-zero values in between the symbol samples. But it still gives you the appearance of the waveform. It's probably not true exact, because no one would do this. No one would actually reconstruct the full waveform. But I do that kind of as a way of seeing an idea of what the waveform should look like. So, and that's what you're plotting at the end. At least that's what I'm plotting, because I do that upsampling right in here. I upsample, and then I have this Z, and then I go ahead and resample it again at the optimum timing point. So these values, this D hat, is no different than what it would have been inside the equalizer, because I'm using the same filter coefficients.
Right, so you're kind of doing a 2-pass approach of computing all of your DFE coefficients and then filtering the entire signal with it so that you can get a continuous waveform.
Exactly.
Just getting at sampling instance.
Symbol instance, yeah.
Okay.
And another thing that's kind of a cheat on this, but it's certainly a possibility, is that when the equalizer gets to the end, when the DFE function gets to the end of its data record, it takes those values of A opt and just freezes the filter. And now those values get get used to process the
Right.
entire original
It's
waveform.
like you train on the first pass and then you use the optimum filter on the second pass.
Yeah, exactly.
Statically.
Yeah, a real system probably wouldn't do that either. It would probably be doing it on the fly, but a real system also could choose not to keep updating at every symbol. It would maybe do it at some sort of intervals, and then it would get a new update. So, yeah, it's just something to play with, though. This is a toy in a sense, that it's just something to play with, and I wanted to get more value out of it by having, like you said, the continuous waveform.
Sure.
And I think if you were building an instrument for a customer, I mean, doing something at Keysight with one of their tools, they might do something kind of similar to give the customer a waveform rather than just points.
Yeah.
But the scatter plot is still actually very useful, and that's legit. That's totally what it is, and that's what I included here.
So I assume that just my timing parameter is wrong.
I'm thinking,
That
I mean,
would be
I
wrong by ISM.
yeah, I did debugging. You might decide, if you're not going to use the debugger, you might decide to just hack into this and take different things out of it. I mean, you can always change the return values temporarily
Yeah.
to get inside of it. But
I guess I'll get it as good as I can and give you what I can.
so I just want to comment on this, though. So this is the decision directed without any noise. Does better than the decision feedback without any noise. They both remove the rotation. So my suspicion is that the hard decisions are, well, the hard decisions in the decision feedback are you're not putting as much noise into the inputs of the LMS, so it should have a cleaner, gradient descent, because it doesn't. The feedback taps are made on hard decisions, right? But it doesn't. It's not true analog. I mean, it doesn't have as much variability inside of it in terms of those samples. So I think that's the reason why at high SNR, just the decision directed does a better job of converging than the DFE. But then when you go to a lower SNR where you have taps that, when you have the whole system running with more noise, then the taps that are controlled by the decisions, and this is the nonlinear operation, they don't have as much noise on them, so people write about the fact that the DFE is better because you don't have as much noise in the LMS. But I started looking at that for a problem. I wasted a bunch of time on that, and that's why I said down here there's no need to do BEP measurements. If you wanted to, for your own curiosity, you could do that and just see which one is better. I'm not so sure the DFE will actually be better. I tried to do that, and it didn't seem to work any better, the decision directed. But maybe now that I have this part working, I could go back and look at it. But that's the whole business of the class. There's so many things to go off and do. You don't want to spend all our time on one thing. So you've got yours working now, and you're reproducing pretty much what I'm showing.
For this code?
Yeah, for this problem. Okay. There's something
Yeah.
that's happening, and
I finished the entire rest of the exam, so I just need to spend some time.
yeah, and that
this
was
afternoon and figure out what's going
yeah.
on.
Another thing that I would do, I would take the original code. That's why I reposted the equalizer's notebook that doesn't have the modifications in it, and just go back and run that for BPSK. That's the reason why in my code I put a switch in there, so I could just switch between BPSK and QPSK, because I was having problems, and it wasn't until I actually put the switch in my code that I was able to resolve my issue. And I don't really even know what the issue was. I tried to write a complete standalone version, and I don't know whether it was something in Python and the shared workspace that was making variables get confused, but it wasn't working. And then when I integrated the QPSK right in the same function file or function that the BPSK was in and put the switches in, then it started working. So I'm thinking that there was something going on in the workspace, because Python shares the workspace, right? You can have multiple functions defined, and there's variables that are shared, and that was kind of the secret to my success. I just blew away a function that wasn't working and integrated everything into the one that's in that equalizer's notebook, and then it worked. So I don't know if that will help you at all, but it was very mysterious, and I really don't know what it was, because I got it working and I just said, okay, I have to move on. Sometimes things like that happen. I wish I knew what it was, but I can't answer that. Okay, so any other questions? This one is graphical. That one's just to say that you understand how it works.
No.
The gray coding one is a little bit interesting, and it's just kind of to see how gray coding can be done. The gray coding in my functions was not done with a generic formula. It was done with a lookup table. So I have a lookup table loaded into the MPSK gray encode and the QAM gray encode. I just couldn't get that to work any other way when I was writing the code for my Com1 class, and I decided I would just leave it the way it is. It wasn't until I developed this problem that I realized that there's a discussion on the internet about algorithms, and this is a recursive scheme for doing the gray code. And I thought it'd be interesting for you guys to know that something does exist, and that's what you're doing with it, just kind of playing with that. Okay. So where we left off was spread spectrum, and we were looking at direct sequence, which was the pictures here. We looked at that last time, and then the second type is frequency hopping, which is where you take some type of modulation. Generally, it's non-coherent modulation, and you have a frequency synthesizer that just hops the carrier around to different locations. And in the beginning, when people were doing frequency hop spread spectrum, they generally used a non-coherent modulation scheme because there were issues with the synthesizer not being phase coherent. So the synthesizer would hop to a new frequency, but its phase wasn't necessarily repeatable every time it hopped, so you wouldn't maintain phase continuity when you de-hop the signal, and then that necessitated having a modulation scheme where the detector in the second block diagram there is not needing to recover the carrier. And I guess you can think about that and say that could be challenging. I mean, if the carrier is moving and it settles a little bit, if it was a frequency, a phase lock loop-based synthesizer, it has a little bit of settling and it has some phase in motion when it hops to the new frequency. But direct digital synthesizers, which use accumulators, phase accumulators and things, they work differently. They can be a lot more precise, but those weren't available in the beginning because people just didn't have fast logic to do this, and they had analog, voltage-controlled oscillators that were being tuned with analog signal processing things, and so there was this non-coherent behavior. Honestly, I don't know what Bluetooth uses or GSM exactly uses, but so now we're going to model a little bit of the DSS. There will be some homework problems on it. So common modulation schemes would be just straight BPSK, QPSK, or it could be MSK. It could be QAM, but the ones I'm most familiar with seeing are BPSK and QPSK. So the model for the transmitted signal would be multiplying the carrier by the ordinary data, which if it was binary, it'd just be plus and minus ones. And if it was a binary spreading code, those would be plus and minus ones. What's special about these, of course, is D of t is at the bit rate, and C of t is at the chip rate or the spreading code rate. So one is a much faster switching signal than the other. Generally, though, C of t is an integer multiple of the bit rate. So it might be 1 megabit per second, and it might be 10 megachips per second. So the spreading code to bit rate ratio would be 10 in that case. So assuming that the spreading code and the data pattern are independents, then the autocorrelation function of this spread spectrum signal looks like a power scaling factor a squared over 2, the autocorrelation function of the data pattern, and the autocorrelation function of the spreading code pattern times cosine omega c tau. This is making stationarity assumptions too. And if we assume that we have rectangular pulse shaping, and in the case of spread spectrum, it's not like in wireless cellular where you want to be very bandwidth efficient. Spread spectrum is kind of the opposite of that. You want to be very bandwidth hogging. You want to just spread your signal way out. And what spreading the signal out does is it makes the energy spectral density of the signal drop down right to the noise floor and below. That is exactly what you want to have. You don't want to have the spread spectrum signal stand out and be noticeable. You want it to be kind of hidden. So spread spectrum signals have a characteristic in the government or military operations known as low probability of intercept, or LPI, so you can't really even intercept the signal easily, and low probability detection, known as LPD. So put together the power spectral density. In this case, we would have the spectrum of the data would be a TB sinc squared TBF, and then for the code, spreading code, TC sinc squared TCF. So those are going to be the two patterns, and when we use our Fourier transform theory for multiplication in the autocorrelation domain, it becomes convolution in the frequency domain or PSD domain. And if you assume that 1 over TC, which is the chip rate, is much greater than the bit rate, say a factor of at least 10, then when you convolve the data spectrum with the chipping or code spectrum, spreading code spectrum, it's like the data looks like a delta function with respect to the code spectrum, so you don't really see anything but the code spectrum. Does that make sense? The idea of a delta function convolving with anything gives you that anything back again. So that's why that approximation is in there, to say that it's predominantly just this guy. So if you write out what the spectrum then is, it's positive and negative shifted spectrum of the spreading code, and that would be sinc squared with the TC in the argument so that it's got spectral nulls at 1 over TC, plus and minus 1 over TC, or the width of the spectrum is centered on the carrier is twice the spreading code rate. So if it was a 10 megachips per second waveform, then it would be 20 megahertz wide. And that example is GPS, actually. GPS has two different spreading codes. One's called the CA code. We're going to look at that in detail here in a little bit. It's at 1.024 megachips per second, and then the high rate code used for military operations is 10.24, so it's a factor of 10 faster. So its bandwidth would be around 20 megahertz null to null. So a big important thing with spread spectrum is in order to recover the data bits, you have to despread. And the code pattern is generally very, very long, so that even if you think you knew a piece of the spreading code, the code might not repeat for days or months, a very, very long time. So finding the proper alignment in that is non-trivial. And in the second generation cellular that used code division multiple access, every cell phone that does CDMA, and I guess I don't think about it anymore, but my cell phone still does CDMA, I believe. It has that standard still supported for situations that a cell site might have it. Everybody got, there's a very long spreading code, and through your, let's see, what's it called again? Your SIM card, right? The SIM card that's in your phone. That was unique to you. I mean, there was, I guess maybe the number of codes that they could give out through the SIM card is finite, but it's spread around the world so that no one would have the same spreading code. And the spreading code that you get is not really a spreading code. What you get is, this code is really long. Just think of it stretching from way over there over to here.
Maybe like a starting position.
Yeah, a starting position is what you got with your SIM card. Does that make sense?
Yeah.
And that's you. That was your identity with your SIM card, where you are in that spreading code.
I can imagine, yeah, it's the same sequence, but it's I'm gonna start from here.
Yeah,
Start from
yeah. But then there's the gold codes, which are used too for the that are part of that too. So there's two layers of coding, but the long code in second generation CDMA is the one that carries the processing power of the spread spectrum. And we're going to talk about multiple access after we just go through some more properties, but we'll get into, two primary applications of spread spectrum. One is the multiple access, but the first one is the anti-jam capability. So then this other bullet in here, since we've been talking about synchronization, now we add in another layer for spread spectrum, and that's spreading code acquisition and tracking. And unless you're using spreading for power management, spectral density management, which is what some systems do as well, you generally don't have a high enough signal to noise ratio to do anything until you can get spreading code synchronization, because that was the original military purpose of it, was to make sure that no one would even see the signal and know anything about it unless you had the magic key, the spreading code, to unlock it. And then to do that, you have to align it properly. And if it's running for months or a year or whatever, how are you going to do that? You can try, even if you got your hands on the code, you can try, but you're going to have to step and search, because you're looking for correlation, and you have to get generally within plus and minus, less than plus and minus the chip period before the signal starts to correlate and pop up above the noise floor such that you can detect it, and then try to dial that in with a tracking loop. And we'll look at that here too.
So that's what's done is a moving correlation.
Yeah, a sliding window, but it's a correlator. We'll look at that because I have a really neat project from DSP where I built a complete tracking system, and it's a project that I don't think I'm going to use this year, but I've loaded it in here. I also have another nice project that's actually on GitHub. That's the tracking side of it. It's not the tracking loop, it's the Kalman filter side of it, where you're actually getting position estimated. And in that particular model, I use SGP4, which is one of the propagators that's available for Python, satellite propagator, so I can put up the ephemeris information for the GPS satellites from back in time, from the sample that I ran. And then you can propagate the satellites and do all that stuff too. We'll maybe look at that too, because that is a GitHub project that's out there. So now we'll add in the despreading operation, we're going to, this is the local code, and then we'll have noise present, and the noise at the receiver front end also gets multiplied by the local code. And delta is the synchronization parameter, which we have to dial in to get it aligned with the received signal. And getting it aligned with the received signal is what I'll look at in the GPS application. It's never going to be stationary because the satellites and GPS are always moving, so delta is what makes GPS do its thing, right? The time difference of arrival is what we're doing to get the position location. And hence spread spectrum, I guess, has a third application, and that is ranging. So it's used for ranging a lot too. Most satellites will have a ranging telemetry system set up so you can range, the satellite can range itself to the ground, and it's a parameter that gets estimated and is used in part of the command and control. Like, where is the satellite? How high up is it? Has it moved in? Has it moved out? That sort of stuff.
So does that mean these kinds of signals, I don't think these kinds of signals get used much in radar, do they?
Spread signals do get used. I'm not a radar person now.
Okay.
I mean, but yeah, anything that can be unique for target tracking and detecting. So spread type waveforms, and then you want to design a radar waveform so that it can be more obscure and not be found out, so that it can get jammed or something like that.
So I think that naive radar uses chirps.
Yeah,
so it
CW.
has a spread,
Yeah,
FMCW.
yeah, exactly.
But yeah, I guess spreading codes could be used similarly to have a broad spectra and be less visible than
Yeah.
chirps.
Yeah. Did I show you my chirp project? That's not on GitHub, but I guess
No, I don't
I've
think
sent
so.
it. It's an FMCW simulation model that I created for a design team that was, they took an automotive radar from NXP, and the company that sponsored them was wanting them to try to use the low-cost automotive radar to detect drone presence, because drones have little tiny fan blades on them, right? So I kind of enhanced and I created an interesting little model where I had, I was doing a sort of electromagnetic modeling. I was modeling something that would reflect RF energy back to the FMCW, and I gave it an attribute that was, I modeled a blade, and I assumed that as it spun around, it would have one point of reflection, and then I can control and position that, and then the FMCW radar could see it, and then I created a nice image to show how that is unique from just a target, like a fixed target, versus something that's got a highly spinning blade on it.
Yep. And you can like see the blade flash move.
Mm-hmm.
Yeah.
I don't know what they did with it. I wrote it in Octave, though, so I haven't converted it to Python. I had promised that I would put it on GitHub as Python, but I haven't done that. It's just sitting, I have it sitting around. I did it in Jupyter Notebook, though. I just did it in Octave, because they were a company that required, the company that sponsored them wanted them to use MATLAB. But I used Mathematica actually to get my geometry model. I modeled the position of something at a distance that had three-dimensional geometric properties. So I got the range. Then I wanted the range of that, which I can use standard geometry, right, to get the square root of the sum of the squares of the x, y, and z components. And then I wanted that in terms of radial distance and two angles. So I decided to do it in terms of azimuth and elevation angles. But then, because I needed to get, for Doppler, I needed to get R dot. It was a fairly messy algebraic thing that I had, and I just let the symbolic capability of Mathematica at that point, because I was doing this rather quickly, do that derivative. And then I could code that into my simulation for the target. It's kind of cool. I haven't done anything with it, though. It was just, it's kind of a process of how you do things, though, if you want to model something. And I've never really been asked to do much stuff with radar, so I just use basic understandings that I have. And geometry is a powerful tool that we learned a long time ago in high school or whatever, modeling using geometry and then trig and so on to convert it to different forms. I think I might have it on here, but I'm not sure. Since I just talked about it, maybe I should look and see. It just so happens I do. Since I talked about it, I'll show it to you since it's kind of interesting. So you can see that this was produced in, I exported the notebook out to Markdown, and then I just use our standard tool. Where is it on here? I'm forgetting the name for a second, so I need to refresh my memory. Typora. I use Typora. So this system is not nearly as sophisticated as a communication system is, but the thing about it is that it's at 77 gigahertz, so it's millimeter wave processing, and the return gets processed by mixing in a very high frequency millimeter wave mixer, and then you get the in-phase and quadrature signals out of that, and then you can take those through a low pass filter and take the baseband component and do FFT processing on it. So, and I took this out of the book that they were using for their reference. So you can model, and an FMCW is a chirping type system, so it does have a chirp that gets created because that's what's getting transmitted, and it does that periodically. So I modeled the single target case. You have to do FFT processing in 2 dimensions, the chirp index and then the Doppler index. And I did a simple test with a radial velocity test. FMCW radar doesn't have a moving antenna. It's just simply broadcasting a bunch of millimeter wave frequencies, just radiating them out, and I just assumed it was a point source so that it would be sending a spherical wave out from the point source into the field. And anything that's out there in space is going to send back a return, and it's only going to send back a return based on its radial distance. It doesn't know anything about is it up or down or is it left or right. It just says I'm transmitting from here, and it's just going to look at that radial distance out, and then it's going to look at the Doppler or the velocity of that target out there. So here, I think in my example, I just used a certain radial distance plus the target is closing with some velocity v naught. I mean, my car has this. Either of you have a car that has the radar system on it. Newer cars have them. Okay.
But I've seen them.
Yeah. Mine uses it for cruise control, but it's also always running, so sometimes there's a certain part of my neighborhood when I come around some curves and I'm doing some things. If a car is parked in a certain spot, it will pick it up and the lights just flash up like collision imminent. And it's like you're supposed to hit the brake, and it throws up this big, huge alert, and then it goes away, and then I go by and nothing happens. It's like it gets faked out. So.
Well, a lot of driverless cars are looking at using radar.
Yeah.
Which is why I'm learning about them.
Okay. It is interesting. So here is the modeling. The Doppler is the standard equation, 2 times. This is for round trip, because that's what Doppler is, right? If a target's coming at you or going away, its velocity or its range is going to be twice, because it's going out and coming back again. So that's where the 2 is. The R dot part is the radio velocity, center frequency, speed of light, and then that's the frequency. So I put in these parameters, go through the processing, and look at the baseband signal. And this is what this gave me. This was 3 simple targets just showing that there is a range based on the model, and then this axis down here is the velocity in meters per second. So that target was stationary. One was moving towards me, moving away, so it has a negative Doppler, and the other one was moving towards me with a positive Doppler frequency or positive velocity. So I converted everything back to the coordinate frame that you'd be in. Rather than hertz, it's in meters per second. So let's see. Then I added noise because they were interested in noise. So it adds speckle noise. I mean, it was Gaussian noise, but it just clutters things up with the noise in the system. So that's that. Then my model, which is the next thing. This was my model. So I called this a point target containing a circular orbit. So it's a target that's out there at a certain range, but it's got a little tiny blade on it, so it's rotating, and the rotation can be, in any orientation, just like a drone would do that, right? It'd be hovering around out there. So I wrote out the equations for that. The period of the blade was t, and then 1 over that would be the rotation rate times 2 pi. And then I gave it an arbitrary phase angle, and that was how I started. Then I did some coordinate conversions, and then I ended up putting into Mathematica the range equation, and then I had it do the range rate for me, and then I had it simplify r dot. So that's
very simple.
pardon me. You find that kind of interesting? I mean, it gets messy in a hurry when you do something like that. So I let it do that, and then I just wrote that into code. So the numerator is the first thing, and then the slash, and then that's the denominator underneath that.
I was just joking. I was saying, yes, that's very simple.
You think it's simple, or I mean, it's got a bunch of terms in it though, just the same.
Never mind.
Or you're being
I was
facetious?
being sarcastic.
Yeah. Okay. Well, I don't know. I mean, if you work in electromagnetics or you work in advanced,
Maybe this is simple to some people.
yeah, it's messy enough. But I tested cases in it, and I'm pretty sure the math is right in it. And then I had Mathematica. You can animate things.
Oh, I see.
So I drew a picture. This would be like the emitter, and then it could be rotating. In that orientation, I could spin it. I could put it in different precessions. So, and then I created a function in, this is in M code or octave code, and I just wrote all those things out that you saw from Mathematica. If you've never had to do this before, these things do happen, and you just, you go like that. I'm going to press forward, and hopefully I won't make any typing errors, and you can test your case. So that example is in here too, and for that example, I just looked at what I was getting in terms of Doppler frequency over a 256 chirp frame, and I see some motion. It's sinusoidal kind of motion for the plane I was looking at, and I ran it, and this was kind of like at a particular velocity. I had to spin the blade pretty fast, but it's that broad chirp there is what I was getting. And to me, I stopped right there because I was helping these students out. I was just like, see, there is a feature. The idea is feature extraction. Like if you're going to do pattern recognition, you're looking for something that kind of is special to say, oh, there must be something in motion, and it's close, but I didn't really analyze that in any detail. But I may have a student that was thinking about FMCW for something, but I just thought that when I saw that, even I may have made a math error, but I was expecting something like that. What do you?
Yeah, like
We've all had physics, right? So what would you expect from physics? That if you get the right reflection off of the blade, and I was assuming an ideal point source reflector. I mean, it's not going to be a perfect reflector, but it's still going to reflect energy back. I was assuming I'd get something kind of like that, where I would see a chirp return because the blade is spinning.
I was reading like driverless cars are using things like this to try to distinguish like people versus bikes versus cars.
Yeah.
Because you can then, you can see like the spinning of the like legs versus spokes versus a car looks more like a point source than either of those really.
Yeah, and it's exciting though. I mean,
Yeah, it's,
You have your topic for Dr. Semiari. You have your topic. I don't really necessarily want another topic, but I could see this could be kind of exciting to do something with it. And especially since I have a car that's an early generation. I mean, it's a 2017 car that I know is foilable. It's not perfect. I mean, the one incident I pointed out to you is one bad thing it does, but when I have the cruise control on and I'm going down the highway and it's curving like this, and if there's an off-ramp that somebody's taken and they're braking heavily, this cruise control will say, oh, you're going to hit that car, and it puts the brakes on really hard and slows me way down. Yeah, even though this lane is totally empty, it gets faked out by this car that's kind of in a close angular view.
oh,
That's annoying.
I can imagine that.
But if you're in a platoon of cars and there's somebody braking right in front of me, I used it last night when I came home from Monument, where my mother-in-law lives. It hit the brakes hard because somebody, 2 cars in front, was slowing down, and it does cool stuff that you'd expect. If your lane of traffic slows down and that's the new speed, your cruise control is set up here and it just brings you down smoothly, and now you're going to follow at that speed and you're going to stay at that. If it speeds up, you'll go up. If you change lanes, like I want to go around these cars, as soon as you change lanes, it gets a clear view. The heads-up display says nothing in front of you, and it just brings your speed back up again, which are things. My wife has a newer car, and her car is a Honda Accord, and it works really nice. It beeps at you when you're engaging somebody that's going slower than your set point, so you're supposed to, I guess, change lanes if you can do it clearly, and then it beeps back again to say I've lost lock, and then your speed stays about the same. So now when I drive that car on the interstate, it's kind of like my theory is getting thrown under the bus. If you're behind a truck that's it's running slower, you're coming up on them, somebody's already in your left lane, are they gonna throw you under the bus and force your system to just slow you way down before you can pull out? I don't know if that's a kind of a crude term, but thrown under the bus is like you're not going to hit the car, but you're just going to have to slow way down and decelerate.
That happens with real driving too.
What's that?
I said that happens with real driving
Yeah,
too.
you call it getting thrown under the bus. That's what I call it.
Fair enough. But yeah,
But
it's interesting. Yeah, the looking at target signatures.
yeah. Do you want to change your topic?
Yeah, I think I'm good.
I don't have one of these radars. I mean, they had it, and they took it with them.
I just read about this stuff like on the side.
Yeah, okay. So you know I have many interests, and this is just an example of how I get distracted with things. And let's see.
Sorry about that.
That's okay. I like to talk about it because this happened during COVID. I did all of this stuff during spring 2020 when we were under lockdown, and I presented it to them, and I thought they might use it, but everything was locked down, and they did, everything was virtual. So I met with them virtually, and they presented their final presentation, and they didn't really say very much about it. And I said, you can use this, you can use it at work, but it's my code and it's my simulation. I maintain rights to it. I mean, but I don't know if they ever did anything with it beyond that. They had their problems, and they weren't as mature at understanding things, and I got really interested in it, so that's why I wrote it all up. So now, getting back to spread spectrum, we have, under perfect synchronization, we'll despread, and we'll get back to data waveform, but then we're going to get this n prime, and n prime is going to be n of t times c of t, the spreading code, and then the carrier frequency is also in there. But a simplified model is to just represent n prime as a Gaussian process with zero mean invariance that is n0 times tb, the bit rate. So because we're, let's see, sampling instant, that's n0 tb. Yeah, so I'm trying to understand why TB is in there. I'm not sure that's right. Right now I'm questioning that because I didn't get a chance to study this. Oops. I have to think about that right now, but it is a spectral density, noise spectral density, and so the direct sequence spread spectrum signal doesn't really modify the spreading code doesn't modify the additive white Gaussian noise. It's already white noise, and then multiplying it by a spreading code, it doesn't really spread it out or collapse it down. It just kind of makes it look the same. And so the error probability is the same. But now we've pulled the signal up, that's when it's D-spread. So maybe that's why I had the TB in there. Maybe it was. But I don't think so, because A squared TB would be there already from the energy detecting of the matched filter. So I think, as I'm thinking about this, I'm thinking that's not supposed to be there. But I can go back and look in the book, because I know he talks about it in the book. So now the next case is we have a jammer. So we have a continuous wave jammer. The continuous wave jammer has got an amplitude AI for interference, and then rather than giving it a unique frequency, it's given a frequency of delta of omega relative to the desired signal's carrier frequency. So then we can put that up along with the noise. The spread noise is the n prime as before, and now we have the interfering term, but it's going to get spread out because it's going to get multiplied by C of t. So the single tone jammer is another name for this type of interferer. So it's a tone at some frequency offset for the carrier, but it gets D-spread. It gets multiplied by the local spreading code C of t, and then it spreads it out into a wideband signal. So if we assume that delta of omega is less than 2 pi times RC, and that's just to put the jammer in the passband of the receiver. So I'll try to draw a picture of that. So it means it's lying in the main null. So now it's significant. If it was outside the main lobe, then the basic modeling assumption would be it's not really going to do much damage at all. But if it's in, then that signal gets spread out, and it casts some energy into the D-spread desired signal. So the model says that the decision statistic has the bit energy, A times TB. It has a random variable due to the noise, and then has another random variable due to the interference. And if you model that out as thinking we're doing an integrate and dump, you can model this as being a Gaussian approximation. I'll try to justify that in a simplistic way. C of t is a plus and minus 1 sequence of random variables, and of course cosine is just going to be some values that can run between minus and plus 1. But now the integration action is like a low-pass filter. So the idea is that for thinking of the central limit theorem, a bunch of random variates all added up of similar variance, it's going to tend towards a Gaussian distribution. So that's the simplifying approximation here. So you'd say that Ni is approximately Gaussian, has zero mean, and has a variance that is TC/TB times AI squared over 2. The TB is from the integration. The AI squared over 2 is the power in the cosine that's getting integrated, and then the TC is related to the period of the chips. I think he develops this more in the book, and if not, it's in some papers. So we assume that we have independent Gaussian random variables impinging. So we have the noise, and then we have the interference. So I'm just going to assume that they're independent Gaussian random variables, so they add together and they create an effective interference component of noise, wideband noise. And you know what's happening here is that I'm trying to draw this so I can see what's going on. So the noise floor is sitting in there. It gets multiplied by a spreading code, but it doesn't really alter its wideband behavior. And then the jammer gets spread out, so approximately it looks like some white noise that's sitting in the bandwidth of the despread signal in red. So you've got the green and the black are the noise components that are being additive in this model down here. So that's the denominator, the effective power that gets captured in the signal spectrum bandwidth, and the effective power that gets canceled from the interference. And GP is the processing gain. So GP is the ratio of the bit period to the chip period, or it's the inverse. So it's the ratio of the chip rate to the bit rate. So in the GPS I was talking about, it's really very, very large because the data is at 50 bits per second in GPS. So it's 50 bits divided into 10 megabits or megachips. So the processing gain for the really wide signal is really, really large, and for the commercial one, it's going to be 1.024 E6 over, let's see, over 50 hertz. So that's, just call it 100 hertz. So that's going to be a processing gain of around 10 to the fourth, which is very, very large. This is for GPS.
I guess to maybe if I can restate simply, the jammer is going to get multiplied by CFT, so
It goes from,
right.
gets spread out.
So you concentrate back your received signal and you spread the jammer.
Yeah.
That makes sense.
This was the big selling point of direct sequence spread spectrum. So now what type of jammers makes spread spectrum more vulnerable? CW is good because it spreads them out, but you can have a barrage jamming, wideband jamming. There's a whole suite of jamming types that systems get tested against, and so the CW is the easiest one to analyze. We're not looking at the other types, but barrage jamming is where the enemy is just sending broadband noise at you, but it does it in a pulsed fashion usually because they have to conserve energy. They can't just keep that high power up. But there's all different types of scenarios that people can use for jamming and jamming effectiveness. Everything, though, costs the jammer something because they have to have resources to do that, whereas the CW is pretty minimal, and the CW is where it's the most effective to do spread spectrum. CW can hit a narrowband signal hard and decisively. I mean, it can wipe it out. And unintentional jamming is what we also talk about too, right? That's why we have frequency hop systems for Bluetooth and GSM, because it wasn't an intentional jamming, it just was happening, and So frequency hop worked pretty good for that. But second generation code division multiple access was an intentional overlaying of signals, and because they had unique spreading codes, they have the same property. The signal collapses, the signal of interest collapses, the signal not of interest, all of them stacked up just stay broad spectrum. We're going to get to that case next. So this is the approximate equation now, and there's games you can play with this model then, where you can rewrite it into that second form, saying it's the signal to noise ratio that the system's operating at over 1 plus the signal to noise ratio times jammer to signal ratio over GP, which is the processing gain. So plotting that out is what the book has in it, and this just shows you, things that can happen. This is the standard BPSK error probability curve. And this is a processing gain of 30 dB, which would be 10,000, or 1,000. 10 to the 3 in power ratio, 10 log base 10 of 1,000 would be 30 dB. So with that much processing gain, and I said the GPS system is getting around 10,000 on its 50 hertz data. You can see at 10 dB it looks pretty close to the standard BPSK without jamming. But then as the jammer gets more and more powerful, it eventually starts creating an error floor. So error probability curves have this tailing effect where they run down and then just flatten out. You can't do any better than that. I don't know if you remember when we were looking at fading channels have characteristics like this too. They set an error floor that you can't go below. So that's true here. Okay, another application is the multiple user environments. This was, in generation 2, code division multiple access, and each user is required to have unique spreading code approximately orthogonal to the other users, and that's where gold codes came in for those that were in a common cell. They were separated. Orthogonality is not perfect. There's some multiple access interference. So the term that's used in these applications is MAI, and that degrades the error probability. Dr. Ziemer had a PhD student that did a really detailed analysis on this for his dissertation, where he got the PDFs of the interference using a lot of convolution, so it was a very messy numerical calculation. The simplified model, though, is called the Gaussian MAI, multiple access interference assumption, and we also assume perfect power control in that case. And power control is something that was needed for CDMA systems because they experienced something known as the near-far problem. Has anybody ever heard that term before? The near-far problem. It's common in cellular telephony. The near-far problem could pertain to, in a cellular environment, and we're going to be looking at cells here, probably after the break, cellular cell topologies and things. We have the base station, and then if one user is much closer to the base station than another user, you have the near-far problem. The signal that's closest gets a stronger signal up to the base station. The signal that's further away is weaker, and that near signal will dominate in the multiple access interference model. So power control says that the power is being controlled by those users such that as they impinge upon the base station, they look at the same power level. So the one that's near is told, bring your power level down, you're too strong, so there's a control channel. It gets the message, brings its power down, and the one further away that's at the edge of the cell is allowed to dial its power up to the near maximum to get received. And then, so perfect power control says all signals at the receiver are at the same level. Does that make sense? And under that assumption, then you can get good capacity in CDMA. And the model for it is PE is Q of square root of SNR, which we've seen before, but now SNR control contains in this model the number of users K, the number of chips per bit, which is also the processing gain, and there I talked about the near-far problem. I tried to say it in words. I think I said that.
Yep. I guess is the idea then, like this, it only has one antenna, so there's only one received signal, so it has to correlate that to each user, right? Individually.
Well, the handset has one antenna typically.
Right.
The base station will generally have two, or at least that's been the model used in the earlier generations. Now we have arrays that can be on base stations, and if we look up behind the campus, we can see examples of that with some of the newer cell sites that are up on the tower, or the new antennas that are on the towers up there.
But I mean, the same base station might correlate its same data against like dozens of users or hundreds of users.
That's right.
So
And it is, as long as the codes are, like the gold codes, nearly orthogonal, then
right, everyone else becomes noise, basically.
yeah, but still the noise stacks up. So that, and that's what this equation is showing you, and this curve is showing you. As the number of users grow, eventually you have the flaring of the error probability curves, and your system is now not able to function all that well anymore. So you reach capacity in a CDMA system. And power control is still a factor. I got to have some experience with this firsthand on a sabbatical I did around the year 2000, working for a company, Paracle Communications. They do a lot of studies of interference for different types of services, but we were up in Denver, and I was in the penthouse of a tall building that was serving out CDMA to out onto I-25 in that area. And there was a power control issue where usually at noontime when people were out going to lunch maybe, or in the morning when people were going to work, this cell site had a problem with power control in that a strong user would come on and it would swamp out everything, and other people could not get their calls set up. And the conclusion to that was not conclusive, but I remember I sat in the with a spectrum analyzer hooked up to the base station equipment. The people I was working with were out driving around in their cars trying to talk on the cell site, but you would see these events where the power control would just go wacky. The signal into the receiver at the base station would just rise really powerfully from, we thought it was one user. And the power control management system is like feedback and control, right? Just like a phase lock loop has control of the frequency and the phase, power control is a control system also, and it can go unstable, or at least it's designed to maintain stability, but there's issues with it always being stable. So it went out of control, and there was a theory at the time, and I may have talked about this already in this class because I don't remember, where we thought that there was a rogue, the people I was working with said they were theorizing there was a rogue cell phone out there, and somebody was out driving around to go to lunch or whatever, and their cell phone was called a rogue phone because they were saying, we were theorizing that it was not responsive to the power control commands, like turn down your volume, you're annoying me, you have to bring it down. And it was just not doing it. And we were theorizing it was either broken or the phone had been modified. I mean, power control is like good people agree that they're going to obey the commands, right? But it eventually resolved, and I don't remember what the answer was. All I know is it was interesting being a detective, because sure enough it would happen, and it would happen for a short period of time. And
can you get the FCC to help you in that case, or what powers
well,
are involved?
I mean, yeah, going after somebody, but it's figuring out where that car is and who it was. They were theorizing, but we are also theorizing that the power control system was going unstable, and it might have not been just one user. It might have been just a scenario that it kind of lost its ability to maintain power control. Interesting though, right?
Yeah.
We know that systems don't always work, and I know the microwave oven in my house definitely interferes with our Wi-Fi. So communications engineers have to face reality. We make great things, but sometimes you can't explain why it's not working right. It just momentarily does something. So their confidence gets shot down when that happens, but I just sort of, smile about it. It's like, okay, now we have something to work on. And Qualcomm is the company that perfected it. They're the ones that brought it from the military classified environment to a commercial reality. They worked tirelessly on getting it to work efficiently in second generation. They became a very, very rich company. They're now a very rich company. They're doing cellular radio, handset chipsets. My Apple iPhone has a Qualcomm 5G chipset in it. I got it last December. It's one of the first that came out for 5G, and it's Qualcomm. They're usually at the forefront of a lot of things. They're big, and they stay big by staying engaged. And I'm sure Keysight sells them a lot of test equipment too.
Yeah.
Does Dr. Semiyari ever talk about Qualcomm?
Yeah.
I worked for them in patent litigation things too. I don't really recall, but I can't talk about anything that I worked on, but I've worked for them indirectly. I worked for patent attorneys, but they were people that were being paid by Qualcomm.
Yeah, a lot of those kinds of companies buy our larger bandwidth products or our more expensive products.
Yeah. They need it. I mean, the chip has got to be out, and all these manufacturers are lining up to get their chips shipped to them, and they got to make it. They got to be able to deliver on it. So,
Yeah.
we also have another company right here in town, Broadcom, which makes chipsets for radios and things too. And
I was gonna say they're not related, right?
now, Broadcom was started by a professor at UCLA, who I actually was at a communications theory conference up in Canada many, many years ago, and we were in the same session, and I met this guy in my session, and I didn't realize till years later that he was the famous founder of Broadcom, who later left the university, and I don't think he even owns Broadcom anymore. I think he sold it out, but he's a really smart guy, entrepreneurial guy.
Yeah, they're right down the block.
Broadcom.
Yeah.
I know they have interesting anechoic chambers in there, because the anechoic chambers they use for testing handsets and things are small, and they can do a lot of nice simulations with those anechoic chambers. And I think the newer stuff that Dr. Semiyari was mentioning, his beamformer, millimeter wave beamformer, where's he going to put it? I mean, it's going to have to be in a chamber, right, to have a controlled test, or is he going to do an outdoor test?
I don't know, but I don't work with millimeter wave.
Yeah. I would think it would have to be in an anechoic chamber, and I don't know if the chamber that we have up in our building is good enough at millimeter waves. I really don't know. All I know is that if you want to do a controlled environment, I was thinking after he was telling me about it at the faculty meeting last week, millimeter waves are so short, so you have such an easy time of having phase shift and all the other behaviors that will drastically change the ability to form a beam, it's going to be challenging, I think.
I also was wondering with millimeter wave on their practicality, it doesn't seem like they can hardly penetrate into materials at all. So I wonder also about that.
Well, that's what he's got his theories on now from his papers he's written. But still, I think it's challenging, no matter what anybody says. But a lot of bandwidth there. But you know, I don't know. The project I'm working on for this company is the ORAN, Open Radio Access Network, and we're just looking at the 3.3 to 4 gigahertz band. I'm just helping them do some DSP work, but they're sponsored and they're being paid to do this development. And it'll eventually have phased arrays in it too, but they're at a much lower frequency. They're only in that frequency band. They're not at millimeter waves, but that's another part of the 5G stuff. Okay, we have to talk a little bit about code synchronization now. Direct sequence spread spectrum and frequency hop spread spectrum both have synchronization required. So we have two main phases: code acquisition, code tracking. So coarse acquisition is where you're just finding the location of the correlation peak with either the spreading code or the hopping pattern. So the upper block diagram is setting up a search algorithm, having some sort of detector. In this case, it's shown as an envelope detector, where you're just going to move the local code around relative to the received signal, and you're going to have a search control algorithm that's going to move that code in a particular pattern. And then when you detect energy in a narrow bandpass filter, because that's going to be your means of saying, if I get energy in this narrow band, I must have collapsed the signal down, it's popped up, I can detect that it's present. The search pattern, though, or search control is, do I linearly search across the entire record, or do I know that my code alignment is, say, right here, and I'm going to start over here, and I'm going to take some sort of a zigzagging pattern to hope that I'll run into it. I mean, there's different strategies that you can use. And then the more contemporary way is to not go with a single correlator. So this is the poor man's way.
How long are these codes typically? Like, how long would you expect this to take in the real world?
Depends upon, it could be minutes, it could be seconds. I mean, for our commercial applications, it's fast because it's been aided. GPS is also pretty fast because it's aided by ephemeris information. But when you first turn the receiver on, like a GPS receiver that I use for backpacking, it's a small handheld Garmin unit. If I'm sitting here in Colorado Springs and it's been tracking satellites and locking onto them, the spreading code, which I'm going to talk about, I guess, after break now. And then I was to get on an airplane and go to the other end of the country where the ephemeris is all different because it's a different geographical location. Turn on that receiver, it takes considerably longer for it to eventually lock onto all the satellites because it has this local memory based on, I just had it on yesterday, had it on earlier in the day, I turn it back on, it locks fast. Go to another location, it's got to figure that out. And your cell phone should be the same way, but because it's sitting there in your pocket running, by the time you get out of the airport or something and pull up a map or something, it's going to have it already. But it still has to learn that because it's not doing it while you have your radios turned off when you're on the plane, right? So certain military operations, a plane, something might leave a location and it has a priori information about this super secret spreading code that's the code of the day, and it has some a priori so it can get it quickly or get it as soon as it leaves the home base. But if it doesn't have side information, it can be still a needle in the haystack to find it, even though you know the code. And if you don't know the code, then you can't get anything. So it could take a long time. So this, in practice, becomes a bank of correlators. When you have a bank of correlators, then you're doing parallel processing, so you can converge a lot faster. And that's certainly the case in our cell phones. We have many correlators that can be put up in hardware in the ASIC. So this is kind of an old-fashioned single correlator idea. And the direct sequence one is doing a similar thing, only it's hopping the signal around. It has the bandpass filter, which is the narrow band that it's looking to see energy fall into when you've got the hopping pattern lined up. And then it will control the search and clocking to get it close so it crosses the threshold. And then as soon as you get within this half chip alignment, you're up on this triangular shaped autocorrelation function that we've seen before. And you're not totally on the peak, but now you can use a tracking loop to pull yourself up to the top. Here I've talked about the search pattern, zigzag, linear. The simplest search is just a linear search. So you're just starting at some point and you just search along. And since the code repeats, you know, if you missed it, if you started here and the correlation was over here and you're searching in this direction, you just have to come all the way around and start over again. And for GPS, the CA code is 1023 chips long, so it's not that ridiculously long to have to search at half chip steps. So you're doing twice that, 2042, is that right? 1024, 2048, or 2046, two less than that, to come all the way around again and finally get it. And that would be, like I was talking about, getting off the plane.
Trillion.
Pardon me? How many steps?
64 trillion.
Well, no, it's just 2046, right? Steps. You'd have to correlate 2046 times, and the worst case scenario is half of that. Well, the worst case scenario is the whole of that, but on average it should be half of that.
Right.
So this is a formula that appears here from the book, mean time to acquire. And these are the parameters that control it. And this has been studied a lot. So how long does it take to acquire? Yeah, there's a lot. And then there's more advanced algorithms. There's state diagrams with lots of states to go through. There's also false alarm probability, so that you think you're out of lock and then you have to start searching again. So in spread spectrum, you don't want to just go back to searching needlessly. You want to really make certain that it wasn't just a glitch and you missed a detection, so you don't immediately go back to searching. But with multiple correlators, you can be doing a lot of things in parallel. So if you drop things away, say the probability of detection is 1, there's no chance of having a false alarm, then it's essentially half the code search interval where you're stepping with TI seconds across a code off of some uncertainty region in the code. Frequency hop is the same. So I have some nice examples in the Jupyter notebook that I want to go through after the break, but then we will, plus I have my GPS example project, then we'll go into OFDM. So what we're going to be looking at, first off, we'll be looking at this project from the modern DSP class and talk a little bit about GPS and tracking and things like that. And I'm going to try to find my other thing on GitHub. Trying to remember what the name of the project is because my co-author pushed it out there. I don't remember what it is. I'm going to think about it while you're taking a break and try to bring it up on the website. So if you wanted to play with something that does the Kalman filter part, you could do that too. So I'm going to suspend this. The GitHub site I was looking for is called GPS Helper. So,
This yours or just you found it and you?
no, it's mine. I mean, I'm a co-author on it. So
Okay.
here's the GitHub site itself, and then we're going to look at the documents that went up on the Read the Docs pages. This will give a little quick introduction to GPS, and then we'll look at the tracking issues and so on, which is the other project. This was created as a training for a company I was working at, and well, a consulting project a couple summers ago. And I didn't expect it to go up on GitHub, but the guy from the company that I worked with decided to put it on GitHub. So what it was about was teaching people about Kalman filtering and then how it applies to GPS. So Kalman filtering is a subject that Dr. Platt teaches in the controls area, but Kalman filtering shows up in communications and signal processing areas too. It's a controls-based algorithm, but it's still very popular for solving, minimum mean squared estimation types of things. So, I mean, machine learning, deep neural network learning, and all these things are just layers and names that have gone on, on the stack of things that have been around for many years. So this Kalman filtering is one of those. So I'm just going to drop down here to this last part that just deals with the tracking problem. And these were pictures that I got from some reference or something, I don't know. But in the simulation, I used SGP4, as I mentioned, to track or to put the satellites in propagation, and then set up a scenario where I would generate a user trajectory in local coordinates and allow that to be tracked by the Kalman filter. So there's a bunch of background stuff that goes on in here, definitely. Whenever you work with satellite propagators, you've got different coordinate frames that you work with, and then generally when you're working on the ground, you're working with yet another coordinate frame. And the coordinate frame I'm using is, let's see, Earth-centric, no, ECU, is that right? Probably going to remember the name of it. The coordinate frame, though, like I said, is a local frame, and maybe I have it written in here, ENU. ENU, what do you think that stands for? It has to be a right-hand rule kind of a thing. So it's east, north, up. So pointing up. There's also, the opposite of that is north, east, down. So it's just pointing down into the ground rather than up. But because I like thinking in terms of mapping coordinates, I mean, the local coordinate frame I chose to use is ENU. So I'm standing here locally, but I'm getting coordinates from the ephemeris for the satellite, which might be ECEF, or another coordinate frame would be the inertial frame. I never was involved with this until I started doing certain types of consulting work. So all of that was combined together. And what I did with this thing to demonstrate this was like the capstone example for this class on Kalman filtering for those people that have very little math background, was I got the GPS satellites from a website called Celestrak. So it gave me the GPS satellites, the latest ephemeris information for a particular day, and then I could start propagating them forward from that day and play with them. So you can see four tracks on here. The Earth is the blue shaded 3D object, and the red dot on the surface of the Earth is Colorado Springs. I chose coordinates local to Colorado Springs, and I was actually using my GPS receiver from Garmin, because it tells me which satellites were visible on the day that I was creating this example. So each satellite has a PRN code, which is a gold code, but they still refer to it, it's a PRN as in a pseudo-random noise sequence. So my GPS receiver on that morning that I was doing this simulation, and is now hard-coded into the code, which is available on the GitHub site here, was PRN32, 21, 10, and 18. And those are the satellites that you see the tracks for. And this is just a duration of 13.2 minutes. So GPS satellites are low Earth orbit, so they're moving with time rather quickly. And you can see, you know, the trajectory that they're on. But those were the ones that my GPS receiver said were present. And then when I eventually plotted them in this 3D plot, I said, yes, there they are. They're kind of right in front of me. I'm standing here in Colorado Springs, and they're up in the sky somewhere. And I used those then for this Kalman filter example. And I set myself on a trajectory on the ground, and this was the trajectory that I walked. I mean, I didn't actually walk it. I just hypothesized that from the origin, 0, 0, I would be walking east 0.2 miles, going north 0.4 miles, and then come back around. So then I had to develop the equations that would get me, you know, the Kalman filter modeling equations for the extended Kalman filter, and did all this stuff that's documented in textbooks and so on to propagate and track from the pseudoranges. So I get the pseudorange from the data simulated from the propagating satellites, and then I know where I'm on the ground. And then I'm having the extended Kalman filter. I'm just getting down here to the bottom. So I have a user track, and this is just showing the convergence of the Kalman filter algorithm over time. And then this is, given it initial condition, this is just showing, you can see it's a little bit fuzzy. This was at 5 miles per hour for particular parameters in the Kalman filter. It's tracking it very accurately. And then I changed the noise, and I increased the velocity to 30 miles per hour in that case. And so these little glitches are occurring every time I made a 90-degree bend. I was like going 30 miles an hour in a car. 5 miles an hour would be a fast walk. 30 miles an hour, I can't walk or run that, right? I can drive the car. So those little glitches is where I was making the turns. And there it's not quite as good, but it was fun, because it's kind of like what we do all the time, right? We put our cell phone on and we want to see where we are. In my family, we track each other, so if I put my phone up, because we're sharing, I can see where my wife is, where my son is. My other son doesn't share. I don't know. He says he doesn't have his phone set properly, but I don't know. Families can do that. Maybe you've done that, or maybe you don't care to do that, but the iPhone makes it really easy if you create a family group, and then you can share stuff. But I do a lot of running and walking and cycling, so I would get tracks back like this pretty routinely. So this is bringing it all the way down to actually getting a geo, but what goes on behind the scenes is what's talked about in here. DSP and a GPS, signal acquisition and tracking. This was designed for my DSP class, but it talks about the Navstar was the name of the program when it was first introduced back in 1973. Navstar stands for Navigation System Using Timing and Ranging. So this was quite an innovative thing back in time to have geolocation. It was designed for military applications. 24 satellites were common. And the way the basic theory works, you can think of it as intersecting spheres. So if you intersect 2 spheres, you get a line. If you intersect 3 spheres, you can get a solution. And one of the solutions might be interior to the Earth. The other one would be above the Earth or whatever. So you can do better resolution if you have a fourth satellite, because then you can get the elevation on top of that. And that's typically what a GPS would do, is get 4 satellites, and then we can get our height and our X and Y coordinates. And because I've used it a lot for backpacking, I've definitely relied on elevation, because that's really important when you're out in the backcountry and you're going up very high. You want to know, am I at 10,000 feet above sea level? Am I at 12,000? I mean, you can feel the elevation, but you just want, it's nice to know that. You can use an altimeter too, which is a pressure sensing device. But so this talked about gold codes and how we're going to correlate a received code with a local code, and we have to pick the right code because we don't know what satellites are visible, but the data stream that comes across on the GPS, this 50 bits per second, sends the ephemeris data live from the satellite. So you get to know where the satellites claim that they're at right now in time, and then you can use that to make the tracking converge faster. I mean, you can find where the spreading codes are, because you know what spreading code is assigned to that satellite once you pull down the ephemeris data, and then you can lock on to the individual satellites faster. So the locking is what the spread spectrum receivers we were just talking about would be doing. There would be a CA code, which is the course acquisition code, which is 1023 chips long. Its chipping rate is 1.023 megachips per second. So it repeats every 1 millisecond on that code. And the objective is to have your local code or replica code find out the time of arrival of that code at your location relative to its known ephemeris time, you know, when it was sent from that satellite. And then you get 3 pseudo-range measurements from the satellites, and those pseudo-range measurements are referred to here as rho, and they're a function of time uncertainties, absolute times, and then an offset. So the pseudo-ranges is what that GPS helper code is using to form the position estimate. For the purposes of the receiver, we're talking about finding, making a measure of this time, or where the peak occurs, where the peak in the correlation occurs. And so I set up a system based on a software-defined radio. It was just a model of it, but I have the RTL SDRs sitting in my office, patch antenna, and this was motivated by another senior design project that some students wanted to do, and I started writing this up to give them, to say, this is what you're going to have to do with your project. It's going to be really complicated to acquire and track, and I just wanted to write it up, and then eventually I turned it into this project for my class where I got a lot more detailed on it, and I wrote all this code in Python. The receiver looks like this, so you have to have multiple trackers, one that's going to work for each of the codes that you want to combine and track. So for each gold code, you would have 3 of these software things instantiated. These were the transmitters, actually. Oh, let's see. This was the receiver. I haven't looked at this for a while. But I'm combining these signals together, and then going to track the signals, and this is what the tracking system looks like. A combination of signals can come in over here. I can tweak the carrier frequency for Doppler, but I didn't track Doppler with this. But these satellites, because they're in motion, there's Doppler on them when they come down to the ground, and the Doppler changes as they move around as well. But I have 2 correlators running in here. Actually, I have 3 correlators running in here. I have a correlator running on what's called an early correlation, one that's doing a late correlation, and one down here that's doing the on-time correlation. So the way you do the acquisition and then the tracking is you have the on-time correlator, the bottom one, is the one that's trying to see the course acquisition, And again, this would be repeated. You'd have many more correlators in a modern receiver, but this was just to keep it simple, just 3 correlators. So the bottom correlator there is just looking to detect lock, seeing that you've risen up on that triangle correlation peak high enough that you're saying stop stepping the code. So here the code NCO, numerically controlled oscillator, is getting stepped to do a serial search, but once you detect lock, then you stop stepping the code, and then these 2 detectors or correlators, one's running early, one's running late, so it gets it can estimate essentially the derivative to decide which direction do I need to tune the code offset in to pull it exactly into lock. So it's called a delay lock loop, which is a different type of detector than you'd see in an ordinary phase lock loop. It's detecting the delay. It's trying to drive the delay error to 0. It's either too early or it's too late, and that's what the correlators on top. One's the early correlation, one's the late, and hopefully it's straddling with the peak in the middle, and it can just drive it in. And so this delay lock loop discriminator forms this as a non-coherent measurement of energies, difference, and sum, and then that forms an error signal for the tracking loop, which is, nominally an error signal is what's called an S-curve in tracking loops. So it's something like that. The error is going to cross through 0 when it's perfectly aligned, and it's going to be negative when it's too early, and it's going to be positive when it's too late. Just looking at the pictures here. So these are the 3 correlator outputs, the early, prompt, and late. And when you difference them, which was part of the assignment, so that's not shown in here. When you difference them, though, you get that S-curve shape, and that's talked about in here. But that, plotting the picture was something they had to do. But in theory, early and late are like here, and then prompt is going to be right at the top of the peak. And in this case, this is what the loop does when it first starts pulling in. It's switched from acquisition to tracking, and now what's going to happen is the prompt is going to drive up to a strong level, and then the early and the late are going to settle to some lesser value. In this case, the early had a strong correlation, and the late had a weak correlation, and the prompt had a weaker correlation, but then the control feedback system drives it in, and then we're in steady state. And that's what the error signal looks like coming out of the tracking loop, which for control systems, that's the kind of things you look for, right? An overshoot, perhaps, if you've got the damping to set to 0.707, and then it settles. And then pseudo-range calculations are measured in microseconds, and that was just part of the project. They also put noise in. This code doesn't run particularly fast in Python, so in order to do the simulations, they had to start. I had them set up the correlators and the code so that it was like correlation peak was here, the initial search was right here, and it just had to step a little bit before it found the right point. If I would have set it up so that it was on the opposite side and it was trying to slide over, then it would take a very, very long time. And then there was another issue where they have to set the threshold for locking, and this, I think, is a figure I created just to say when you don't want to lock, you set the threshold high, but when you do want to lock, you have to bring the threshold down so it will actually stop the serial search and then engage the tracking loop. Interesting, or maybe not interesting, I don't know. We use GPS so much, though, that for them it was just running the code, doing some measurements, and calling it a day.
I guess I'm curious, how do you pick the satellites you talk to? And how do you figure out, how do you things like
How do you
that?
pick the satellites? So, like I said, initially you don't know anything about what satellites you're going to see out of 24. You need to find 4, right?
Yeah.
So when you touch down, I'm just using the example of me traveling, pulling out my GPS receiver, it's starting from a blank slate. It doesn't know at that time of day what satellites it's going to see.
Because it just needs to find 4 correlations that are different from one another.
Yeah, 4 different satellites. So 4 correlators have to engage on legitimate satellites, and the satellites are always coming and going. So that's another frustrating aspect. If you've ever, you know, I think your cell phone has a display where you can see what satellites it's using, but my Garmin GPS was much better at that because it had a special display that would show me a flat view of what satellites were in view. So you might start with 3 in view, and then before you get all the channels locked up, one of them might actually go away, and then you're now going to be trying to lock to another one. So it's always trying to find more satellites because satellites are always going away too. So it is frustrating. I've sat there in a camp, in a backpacking episode where people yell to me because we're hiking along and we're not sure where we're at anymore exactly. We have our paper maps, but we're not sure. They'd say, pull out your GPS, tell us where we are. So I pull out my GPS and I'm waiting for it to lock. It's probably got 2 satellites, and I'll say it's trying to get a third. Whoops, that one just went away. It's now trying to find this satellite. I mean, you have to be patient. So it has a display where you can see bars, signal strength, and it'll have filled bars, meaning it's locked onto those, and then it will have clear bars, meaning that it knows from ephemeris information that these satellites should be reachable, but it hasn't locked onto them yet. So you just watch it kind of unfold, and then when it finally has enough satellites, then you can switch the display to the map view, coordinate view, whatever, and then you can get your coordinate.
That's interesting.
So our cell phones are a little bit different because what do I do with my cell phone? I just use the map tool and I look to see where I'm at. But when you're out in the back country, I load topo maps onto the GPS, and then hopefully it's pinpointing me on a trail somewhere where I'm expecting to be. And you know, I've been led astray, and people pick on you if you're the one that's carrying the GPS and you say we're here, and then you walk a little bit further and say we're lost, there's no trail anymore, it went away or something like that. People have always really picked on me saying your GPS is lying. I've taken, a few steps off we've gotten a little bit out of alignment, and then we pulled back on again because you're looking for evidence that somebody's been here. And trails are very distinctive in the backcountry. It's either a trail that you can see footsteps on, or it's a rut, or you look for the rock cairns that people have made at certain key points where the trail makes a bend one way or the other. And that's evidence that, okay, this is probably where I want to be, but if a trail splits and you wanted to go that trail, you didn't want to go that one, that's where it helps. So, you get your coordinate, you start taking the route that you think you're going to take, and then a little bit later you check again just to make sure, am I going down the path that I marked on my maps?
Yeah.
You know what I'm saying? You don't want to be backtracking, and if you're up above tree line, thunder and lightning can come in and you could get struck by lightning. So your timing is important too. You can't stay out at noontime above tree line because lightning, if there's storms around, you could get struck by lightning. So you have to plan your day and you have to be about your business. You can't just loiter around and then get zapped by a storm. So
Maybe I'm just bad at navigation, but sometimes, like all the rainwater will carve a path that sort of looks like a trail but actually isn't.
yeah,
And having a GPS is helpful to see, this isn't a trail, this is just like a little river, if you will.
yeah, you're right. I've been on some hiking trails though where they've been trod so many times. I'm thinking of an area up near Steamboat Springs. It's called the Flat Tops. It's a wilderness area where the trail has been walked so much that it's rutted. It's maybe about that wide, and it's about a foot or more deep from tracking it. And when you're walking in that, you have a heavy backpack on, and you're almost having to walk toe to toe. You can lose your balance, and then you can say, I'm going to walk up on the side of the trail. And then people have done that, and then they've rutted that down. So there's challenging erosion things like that too, because you want to walk fast, but you don't want to fall over. It's part of the fun of the whole being in the backcountry. But then you're looking at the clouds, and a bright sunny day can turn into thunderstorm really, really fast. So it's a challenge, but it's kind of what goes along with the whole thing. So hopefully that was somewhat interesting. Throw that one away. So back over here, we're now going to look at, I was going to look at a couple things in here too. I've got,
You said that the homework probably won't be due next week. It'll probably be due on the 6th or something.
yeah, it's just going to be play it by ear. I've got some spread spectrum examples in here. We'll just look at some pictures of just using the tools that are available. See, there's a typo in here. Here I just generated some direct sequence, so I used the PN generator, and I have to repost this because it has the capital letters in it, and the syntax was changed, remember. So here I'm generating some NRZ bits. Here I'm going to use a PN generator. NRZ bits 2 means I get to put in my own code pattern, so I'm using a length 5, or 4 I guess it is, no 5. And I'm going to do 4 samples per chip, and then here I'm going to create data, just random data here, that's 16 samples, so that means my spreading ratio is 4, so it's not really all that great. So that's the data pattern, that's the spreading pattern, and then this is the product of the two. And then this down here is what happens when I multiply by the spreading code a second time. So when I multiply by plus and minus 1s a second time, plus 1 times plus 1 is a 1, a minus 1 times a minus 1 is a 1, so that does what I refer to as stripping the code away. The code is now stripped away by the local code. So this is just all contrived. So here's the spectrum. The underlying data pattern is the blue one. The spreading code being that it's an M sequence that has spectral lines in it, but then when I multiply it by the random data bits, I get this green pattern. So the fact that my spreading processing gain is 4, my transmitted signal has its first null at 4 times the bandwidth of the original data signal. And that makes sense. That's what we've been talking about. I'm just doing this so you can visualize it. So then I put a tone jammer in there, and I set a ratio up called jammer to signal ratio. In this case, I'm setting it at minus 10 dB. I've only got a processing gain of 4, so I can't really make the jammer to signal ratio too awfully large because I'll blow my signal out of the water. I'd need more processing gain. But I still brought it up to minus 10 dB. So there it is sitting in the spectrum. There's the main lobe. Then I've come along here and I've despread, and the important thing to note here is now I will have a noise floor underneath this. The jammer has been spread though. You don't see it anymore. It's just acting as a noise floor underneath this. And then I apply a matched filter, and then because the timing is all perfect here, I'm just looking at what's going on, and this is what the jammer is doing. And as a matter of fact, what I can do here as a little example is I can turn off the noise or make the noise really huge. So I'm going to set this up to say 50. Well, let's see what happened. Did I set the wrong thing? It's now saying I can't broadcast, so what did I do wrong? Maybe it's over N0. I don't want to really spend a lot of time on this. I'll just tell you what it does though. If I turn and make the signal to noise ratio really large, the fuzziness on those scatter points will go away and it will become very tight looking, and that is just the interference, because it's synchronous, so it doesn't really have a random behavior. It looks more deterministic in terms of what the interference is doing at this point, just for this scenario. But the diameter doesn't really change. The noise has made it a little bit bigger, but it's the jamming that has made it look like that. And I have to be able to run this in order to do that, so I don't know why it's not working. Something's not in here.
Well, it's not even running with 20 either.
Yeah, I'm seeing that. But I don't know what I tapped on this. I might have done something unwittingly. So we're going to move on to OFDM at this point. Spread spectrum simulations at the waveform level are hard to create because you have to have the waveform that's the spreading signal, which is at a much higher rate, and then that increases the number of samples that you have to process, and it makes things very slow. I would think, because I'm still tinkering with Julia a lot, that Julia would be much better for spread spectrum simulation because it compiles to faster code. So spread spectrum simulations are not easy to create. So now we're going to start talking about OFDM, and then let me just let you know where we're going to be heading to next, since that's probably going to be of interest. Then we're going to go into an overview of cellular and cell design, interference, and things of that sort. OFDM is a modulation technique that is very popular in cellular, but just onto itself, it's become very popular. And I've got some old pictures in here since LTE was has rolled out the times that I've taught the class. But so what is OFDM? It's gone by different names, and they're very similar to each other. One was originally, when I first learned about it, it was called multi-carrier modulation. And then it can be specialized to orthogonal frequency division multiplexing, and that's the OFDM name. It's very popular. It continues to be very popular. When I first learned about it, it wasn't nearly that as popular as it is now. It's been used in DSL for digital subscriber lines, which is another way that you might get internet into your house through your telephone, twisted pair. It was originally part of WiMAX, which was a standard that was going to be more of a local area network, wireless network 802.16, and it had the WiMAX forum. But I don't really know that that's really going anywhere anymore because, you know, fourth generation cellular came along and now 5G, and so WiMAX, I think, kind of doesn't exist. Have any of you ever heard of WiMAX? Is it still going, or is it kind of not, or is it probably morphed into something?
No, it was for last year.
Pardon me?
It was already used, but now.
It's being superseded, though, isn't it?
Yeah.
Kind of. When I would go to the communications theory conferences, there was just a lot of talk about WiMAX. So then LTE came along, which was fourth generation, and it's definitely a big player in that. OFDM is used in Wi-Fi also, and like I said, DSL. So it's pretty prominent. I had one PhD student do things with OFDM. She was came from Thailand, is where she her government sent her here to get her degree. And she's a professor back in Thailand. So we have one carrier. We're used to the idea of a single carrier system, but with OFDM, you have many carriers, and they're orthogonal to each other by virtue of the FFT actually being used. Or it's actually the IFFT at the transmit side and the FFT at the receive side, and I'm going to try to explain why that is, because when I first learned about OFDM, I thought FFT is always done first, and then you do the inverse FFT, and why do we do it the other way around? So I'll try to explain that. But the bands that I have plotted there as being orthogonal are the idealized frequency responses you would get for each bin in an FFT. They have an orthogonal relationship, though, by virtue of the fact that the FFT center bin frequencies are orthogonal to each other, right? You have n frequencies in the FFT, and the period is n in the FFT itself, so that means that those frequencies are mutually orthogonal, and that sets up a nice way of doing things. So Dr. Ziemer has in the book MCM and OFDM because he came through this transition where people called it multi-carrier modulation, not necessarily orthogonal, which is the top picture, and then the OFDM idea where you're going to do an IFFT, and you're going to take data that's driving each of the points of the IFFT, and then that's going to typically would get a prefix put in there, and we'll spend a bunch of time talking about that. Then you send it over a channel that has additive noise and multipath, so this is one of the features of OFDM. You can mitigate multipath. And then you come into the receiver and you remove the prefix, and then you just FFT the data. So from this picture, you're seeing the IFFT is done first. So you're going to apply the modulation in the frequency domain at these different subcarriers, and that's what the input side in there is. So you can think of data going on each of the subcarriers or each of the frequency bins, and then by taking the inverse FFT, you're getting back to a time domain waveform, which is this OFDM signal. And the cyclic prefix, like I said, we'll talk about what that's all about. That relates to multipath, though, and the use of the cyclic prefix is pretty much standard to mitigate multipath. But then once you take the cyclic prefix away, then you've just got back the original signal that you put in at the transmit side, and then FFT is spectral analysis, right? So it's taking a time domain signal and it's going to break it down into its frequency spectra, and each of the bins of the FFT now contains the modulation that you put on at the transmitter. So it's it looks like a subcarrier at that point. So typically they put QAM, binary, quaternary, 16 airy, whatever, QAM on at the transmitter. It gets converted to the time domain, and that's sent as a time domain waveform, and then it gets transformed back to the frequency domain, and then each of those carriers comes out and contains a serial bit stream that would be for that particular channel.
You said like QAM on each individual bin?
Yes, yeah.
I guess the obvious question is, what's the advantage of this over like...
Okay. I'm glad you asked, because I've got the answer to that. This is a very cool modulation scheme. The first thing is, why would you do it? You're thinking, oh, I have to have an IFFT at the transmitter, I have to have an FFT at the receiver. Isn't that going to be a showstopper? Well, it's efficient. So multi-carrier modulation was not necessarily purely orthogonal, but the idea of OFDM with the IFFT and FFT was being efficient, right? Because we know we can make that efficient. So what's the idea of the OFDM is this next bullet. I think it starts talking about it. When you have multipath, that introduces ISI. So multipath introduces ISI, but if we can make the carriers many carriers, we have a small serial bit rate on each of the subcarriers, so now the bit period is much longer, and we can handle the ISI more readily. It's not going to be as impacted. As a matter of fact, in a gross scenario of multipath channel that's composed of OFDM, you might have a null that's going to wipe out one of those subcarriers. And you say, oh, well, I've got a bunch of other subcarriers that null hasn't taken out. And even when I do have a certain amount of delay spread in the channel, we have this neat trick, which I'll show you, the cyclic prefix idea, which can also mitigate the signal so that I can get rid of the delay spread in the channel. And that's that bullet right there.
So you're saying we have to transition less often so ISI can be reduced?
Yes. And you've got this robustness, because if you did have a two-ray channel, you know, we could have a ray from there and one from over there, and when it comes at us, it's going to put a null at a particular frequency that may land in our band, but rather than having that null wipe out the entire signal, it will maybe only wipe out one or two carriers,
Right.
and we can just get by without those two carriers. So, and I guess other opportunity would be subcarrier power levels can be adjusted independently upon channel, based on channel characteristics. A lot of what you're going to get to understanding this is going to be in the final project/exam. I have a nice exercise that you'll get to work with OFDM. It teaches you about the cyclic prefix, what are called, let's see, I'm going to forget the name, pilots. Yeah, pilots that you can send into the channels to estimate the channel. So the pilot is just allowing certain carriers to be just pilot carriers that help you learn the channel. And then you can unravel things with that too. So the different standards use different pilots in the OFDM waveform, but that allows you to have the channel estimated, because a pilot will come straight through and it will contain only the channel distortion. And so you'll see that in action too. It's all in Python, the way I have it set up. It's actually now part of the Digital Comm module, and it wasn't when I last taught the class in 2018, so I want you to use that newest version, which is already on your system. This is a particular example of WiMAX that I got from some book, I think, just showing how WiMAX was designed so that if you're closest to the base station, you could use 64 QAM and you could get a lot higher throughput, and then as you moved further away from the base station, your subcarriers would contain a lesser modulation scheme. So that's one of the nice things about OFDM, is you can control what modulation gets put on the subcarriers for which types of users. The ones that are close by, it can switch to do the higher density QAM, and the ones that are further away. And a user will aggregate channels. A user doesn't own all the channels. A user owns certain channels, and they can be aggregated into a composite for you, for your purposes.
So you'd be like forced to put in zeros on some of the 50 bins?
That can be done, and my code lets you do that too. It lets you control which carriers you activate. But there's a lot of games, and I can't keep up, or have not wanted to keep up with the standard. But
Seems clever.
this is a map that I just found off Wikipedia. This was a long time ago now, 2014. But this was just the rollout of LTE, long-term evolution, and the underlying modulation on one side of the link is OFDM. That should be removed from these slides. It's just a historical fact, though, that it didn't start instantaneously, just like we're stuck starting 5G right now. We're still really relying on LTE's capabilities and enhanced LTE. I don't know. What does my phone say today? Because I always look at it to see what it's telling me. Right now it's not displaying that information for this site. But generally I see something about LTE or something like that. I've barely got a signal right now. I'm on AT&T. Do you know what the icon is? You see something, it might say 5G E or something like that. I see that in some cell tower sites, but
Sometimes I see 3G on my phone,
okay.
but not often.
So it's coming, and it's just not here yet. But yeah, the thing I'm working on for 5G hails back to reading this standard, the 3GPP documentation that's out there, because that was generated. 3GPP stands for Third Generation Partnership Project. And that was, you probably bump into that, I'm guessing, because it's still, it was a partnership amongst countries and vendors. So standardization is really important. And back at third generation is when they formed this partnership to try to be more unified, and then that led into the creation of LTE to be international as well. It was time to get together and play as one worldwide community for wireless standards. So I don't even know, is there something else besides 3GPP that's out there that's competing with it? Do you know? Is there something other than 3GPP kind of behind everything in today's world for cellular commercial?
Or it's not,
I mean, another standards organization that was formed?
I'm not sure, but I think there is another standards for WiMAX. There was,
Right.
but I'm not sure what was the name.
Well, back in second generation, there was, for second generation, there's three that come to my mind. There was GSM in Europe and elsewhere. There was North American TDMA, which was time division multiple access, just like GSM is. And North American TDMA was also similar to some things from Japan and a few other countries. So there was those two camps, and then there was Qualcomm in their CDMA. So I'm thinking that there were three different technologies that just fought, just,
Would ones
for the.
be like they'd only work in certain parts of the world, or would manufacturers put in multiple
Radios?
chipsets in them?
They eventually started doing that because, yeah, people demanded interoperability because they didn't want to go from Europe to US or vice versa, let's say, and not be able to use their phone. So then that, in reality, who wants to win? The consumer wants to win, right? We want to have the most flexibility. We don't want to have a lot of radios sucking our power. We'd like to have a nice, convenient platform. And so now the companies making these things had to, that's where this partnership project had to actually happen in order to make it, a cost-effective solution
I
and
guess
stop.
otherwise your phone would have 3 chips, or
We have a
be
lot of,
useless in half the world.
yeah, we now have, I don't know how many radios we have on our handsets, but I think it's at least 5, but I'm not positive.
It's
Uh,
several, yeah.
It's a lot. I mean, we have a GPS with multiple correlators. We still have to support GSM, I'm sure. We have to support OFDM, CDMA for some networks.
And then LTE and Wi-Fi are different, right?
Yeah, Wi-Fi is another radio. And then we have 2 radios there because we have the 2.4 and the 5. So, you're just, it's at least 5 radios, I think. And then there's filters to control interference. It's pretty complicated. And Qualcomm is one of the kings at it. There's other companies that have their radio chipsets too. It's a microwave thing. Dr. Kelker's students, he has one student that she just recently joined Qualcomm in San Diego. She's a microwave circuit kind of person, and she's working in the radios area for them. All this stuff has to come together to make it work. So this,
Design at that speed is like black magic.
yeah. This just showed another picture I got on how LTE and LTE Advanced came onto the scene when we had WiMAX and we originally had 3G and its different things that were going on there, and then of course way back when we had 2G. But so we're way out on this line. So a little bit before we have to leave, my wife's letting me know about the move. Okay, I'll have to get back and look at that. My son, remember, moved, came back from Wichita and is living and working up in Denver. He's working at his architecture firm that he joined, but he hasn't been. He closed on his property last week, and now he's getting to the point where we can take the furniture and everything that he moved out here, store it at my mother-in-law's, and move it up. So he's living at a place where he had to get permission from the management. You have to give 72 hours notice and a deposit before he can move into this condo unit. So I think what my wife just said is it can be done tomorrow. I didn't know this morning if it was going to be tomorrow, or tomorrow or Wednesday. So he's anxious. I'm anxious to see that happen. So that's exciting for me. And yeah, the wireless network is supporting that, because my watch is talking to my cell phone and my cell phone's talking to the network. So LTE uses pure OFDM from the base station to the mobile, and there's some other terminology that I'm introducing if you ever start reading documentation, but it's in some terminologies it was called the downlink, as in satellite downlink terminology. But I think a more universal way of calling it is the forward link. So the forward link is from the base station to you. And then they use a different standard, single carrier frequency division multiple access, or SC-FDMA, and that's used on the uplink, also known as the reverse link. And there's more discussion I have on that, but we're out of time. And I see that class is not even coming in today. Sorry, I've gotten kind of carried away with stuff, but we're definitely going to spend more time wrapping up OFDM. We'll talk about the cyclic prefix. I've got a really good discussion I got from another book, motivation behind the cyclic prefix and why the CP works. So you can look at that if you want to. It all has to do with mitigation of multipath, and you will see that in the simulation that you'll work on for the final project. I'm passionate about that because I had this student who did her dissertation with something for OFDM. I should remember exactly what she did, but she had some really novel intercarrier interference study is what she was working on. That's another thing that happens with OFDM, because when you're in motion, everything gets Doppler, right? So when you're in motion, the carriers bleed into each other and you get what's called ICI, intercarrier interference, and you can estimate that away with some algorithms. And she had a novel approach that would do it iteratively that she developed for her dissertation. Because she went back to, as soon as she graduated, she went back to Thailand. I got to go to a wireless conference and present her one of her papers from her dissertation and try to make it sound like I was totally on top of it. It wasn't a perfect solution, but it was another thing I'll just mention right after I sign off, because it's not relevant to teaching.